Hey there, Coach Travis here, and I've got the following problem for you. We've got this crazy function here. I have no idea what the graph of this function looks like, but using calculus, what I'm going to be able to do is I'm going to be able to find the exact locations of the local minimum and local maximum of this function. And well, of course, there might be a whole bunch. So I guess I should make that plural. I'm going to find the locations of all local minimums and all local maximums. So we're going to do that. And it says we're going to use the first derivative test. So yeah, we'll see how that goes. All right. So when you approach problems like this, what you always want to do first is you want to make number lines. So you'll see why this is super important later. So this is part of organizing your work is making number lines. So I'm going to make two number lines. One number line is going to be for the original function. So the original function is h of x. And the second number line is going to be for the derivative. So this number line here is going to be for the derivative. So I want to label everything carefully so that I know what it is. And I got my two number lines. These number lines are going to be very important because later in the semester, what we're going to get is we're going to get the second derivative involved. And so we're going to need a third number line. And so these number lines are very important in terms of keeping your work organized. Okay, so I got my number lines, and you say, okay, so what? What are we going to do with them? So the idea here is we want to remember this fact, or let's think about what's the first derivative test say? So the first derivative test, what it says is that if the derivative changes from positive to negative, then that means that you have a local maximum. And similarly, if the derivative changes from negative to positive, that means that you have a local minimum. So what we need to do to answer this question is we need to figure out, okay, well, where does the derivative change sign? We're interested in where the derivative changes from positive to negative, and we're interested in where the derivative changes from negative to positive. So we need to find where the derivative changes sign. Okay. So, well, if we're going to find where the derivative changes sign, I guess we need to find the derivative. So, all right, so let's write down the derivative. So the derivative of this function is not too bad. H prime of x is equal to, it's going to be negative 6x squared minus 30 x and then plus 144. All right, so there's our derivative. Okay, so we have to figure out where that derivative changes sign. Or mainly we got to find where is this derivative positive and where is this derivative negative? When is it a positive value and when is it a negative value? Okay, so this is a little bit of a hassle, but we can do it. So let's see, I hope I can factor out a negative 6. Let's see, yeah, because 144 is 12 times 12, so 6 certainly divides that. So let's factor out a negative 6, and hopefully that'll help us understand this a little bit better. Let's see, so we're factoring out a negative 6, so we have x squared, and then plus 5x. Oh, sorry, and why am I factoring this again? Well, because I want to know when this is positive and when this is negative. So I want to simplify this as much as I can so that'll help me figure out where this is positive and where this is negative. Okay, and let's see. So then 6 goes into 144, like what is that, 24 times? So negative 24. Okay, and now I look at this and I say, oh, okay, I think I can factor this. I can factor this quadratic here. So that tells me that h prime of x is equal to negative 6 times, okay, let me see here. We want to add to make 5 and multiply to make negative 24. So if I think about, well, let's see, what are the things to get 24? Like 3 and 2, yeah, 3 and 8 looks good. Yeah, I think it is 3 and 8. So anyway, so the point is you can factor this on your own time. I factor it by guessing and checking, and it factors into x plus 8 times x minus 3. Okay, so let's think about what's going to happen here. So what I'm going to mark on my number line is I'm going to mark the critical points. So remember that the critical points are the places where the derivative is 0. So the first thing you do on your number line is you mark the critical points. So I see that from this derivative, I can see that the number 3 makes the derivative 0, and the number negative 8 makes the derivative 0. Oops. And then I'm also going to mark those points on the number line for the original function as well. Okay, so the moral is that these two places, these are the places where the derivative is 0. And those are the only places where the derivative is 0. And so that means the derivative is always positive or always negative on this region. Likewise, the derivative will always be positive or always be negative in this region, and similarly for this region, because these are the only places where the derivative can change from being positive to negative. A function can only change from being positive to negative at a 0 or at an asymptote or at a discontinuity. But this doesn't have any asymptotes or discontinuities. So these are the only places. Okay, so how do you know? Is it positive or is it negative on this region? And the easiest thing to do is just pick a number. So pick a number that's less than negative 8. And I'll give you a pro tip. The more extreme the number you pick, often the easier it will be. So let's say pick negative 100. That's certainly in this region. So if I put negative 100 into this, what do I get? And another secret here is I don't actually care what the actual number is. All I care is the number positive or is the number negative? So if I put negative 100 into the derivative, do I get a positive number or a negative number? And so, well, let's see. So negative 100 is going to make this negative. It's going to make this negative. And the negative 6 is always negative. So it's going to be a negative times a negative times a negative. And a negative times a negative times a negative, that means it's a negative. So I'm going to put a little negative sign here to indicate that on this region, the derivative is negative. So again, the idea here is these problems we're doing, they're easy if you organize your work. So if you organize your work in a meaningful way like I do here, then I think these problems are not too bad. But if you don't organize your work in a meaningful way, then these problems are very, very difficult. So I can't emphasize how important it is to find some system of organizing your work. All right, so now let's pick a number between negative 8 and 3. So 0 is a convenient number in there. So if you put 0 in here, you get negative times positive times negative, and that makes a positive. So on this region, the derivative is positive. So I'll indicate that by putting a little plus sign. And then finally, if I pick a number bigger than 3, like say 100, 100 is going to be negative, positive, positive, and negative times positive makes negative. So that means the derivative is negative on that region. So, all right. So we basically have what we need. We have what we need for the first derivative test. But personally, I don't even remember the first derivative test that well. The thing I remember is this fact, and you'll see what I write on the number lines here, that when the derivative is negative, what that means about the original function is it means the original function is decreasing. And likewise, when the derivative is positive, so when the derivative is positive, like it is right here, then the original function is increasing. So the way I'd solve these problems is I don't really use the first derivative test. I just use the number lines. And I say that, okay, the fact that the derivative is negative on this region means the original function is decreasing. So what I do for myself is I draw a negatively sloped line. And then in this region, I draw a positively sloped line to indicate that, okay, the function's increasing. And then finally, I draw another negatively sloped line here because the derivative is negative. So when the derivative is negative, the original function is decreasing. When the derivative is positive, the original function is increasing. So here's what I draw, and then you don't even need the first derivative test. If you just look at the number line, you can see that, aha, this is going to be a local minimum. Because as the, the function's going down until it gets to -8, and then it goes up. So that's a local minimum. And this is going to be a local maximum. Because the function's going up and then it's going down. So the moral is, so let me summarize this here. So what we have here is we have a local, typo. We have a local minimum when x is equal to -8, and we have a local maximum when x is equal to 3. So that's my conclusion, and so I think that should answer the question. So it's a multiple choice question, and if I'm lucky, that's an answer choice. There is a local minimum at x equals -8 and a local maximum at x is equal to 3. And that is exactly what we found. So I'm going to check that one. And now you don't have to do this, but I always like doing this because it makes me feel good. And that is, you draw the graph. And you might say, oh my gosh, that's too hard. Well, I don't mean draw it yourself, but what I mean is use a computer. So let's use GeoGebra and draw it and see what this graph looks like. So here we go. So I already preloaded it on GeoGebra. So here's the function we were dealing with. And this is pretty cool because if you were to just draw this on GeoGebra, you might think, oh my gosh, this function doesn't have any minimums or maximums. It just looks like a couple of vertical lines. But thanks to calculus, what we know is, well, no, there's something going on at 3. And so what's happening is I need to rescale my axes. And I see that sure enough, when x is equal to 3, we have a local maximum. And then now, if you hadn't done the calculus, you might think, oh, well, this must be it. It's got a local maximum at 3, and that's it. So if you just used your calculator, you might have gotten this picture, and you might have, yeah, you might have circled it. Oh, whoops, wrong thing. You might have said this was the correct answer, because that's all I see in the picture. But using calculus, we know better. We know that actually there should be I should zoom out a little bit more, or rescale the axes a little bit more. And there we go. And I see that, okay, yeah, at x equals -8, there sure enough is a local minimum. So that was a really good success story for calculus. Is calculus predicted a couple of things that we might not have known even if we used a computer to draw the graph.